This screencast is about electrochemistry and finding the cell potentials for those voltaic cells that we just drew. So you're able to calculate the amount of volts that travel. So we saw in our picture of a voltaic cell that we are going to have two different electrodes connected to a circuit with a salt bridge, and that electrons will travel through them. When that happens, each different electrode has a value that is their cell, their reduction potential. How likely are they to become reduced? So when you put these two together, you have a voltage or a difference between them that allows the electrons to travel. If you have an E cell or an E value for the entire cell that you've put together, the two electrodes, and if that value is positive, then that reaction is spontaneous. It'll go on its own. Now, we need to be able to calculate that, and we're going to be looking mostly at E0 cell, which is the standard cell potential because it's at 298 and it's at a specific conditions. Those values are listed in the back of our book in a table. Actually, it's in page 857 or Appendix E, and they are constant. So every time you deal with a specific metal, it's going to have the same cell potential. What you're going to be doing is you're going to be subtracting the reduction minus the oxidation in order to find out what the cell potential is. Now, the reason we do reduction minus oxidation is that's the correct order, but if we've been learning and paying attention, we've been looking at redox reactions, red minus ox. So reduction minus oxidation will give you the cell. You do not, as we have in past cases, when you have, let's say we have 2 zincs being used, you're not going to double the reduction potential. You're going to use just the value that it gives you. And if you end up having to have the reaction is opposite of the reduction potential table, you don't do anything with the sign. You do not change the sign. You do not use the coefficients. I know that's a departure from what we've been doing all along in chemistry, but electrochemistry is a little bit different. So the main focus is going to be on our reduction minus our oxidation to find our cell potential. And you'll find that these are pretty simple. All you have to do is subtract them. Here's an example that's already set up and done for you. You can see that there's a very long, very crazy looking balanced equation. And you also will notice that you have CR over here and we have I. So we're going to be looking for the reduction potentials involving the CR207 and the I minus. And if you look in your chart, you'll notice that the values are 1.33 and 0.536. Now, they would ask you to find the cell potential, and we have to figure out which one is being reduced and which one is being oxidized. Now remember, we have our oil rig, and oops, sorry, a little crazy on my G there. So you'll be able to decide oxidation is losing. We are losing our electrons here, so the I is our oxidation and reduction is gaining, and we have our electrons going in here, so that's our reduction. So we are able to do our red minus ox to find the value. You can see that 1.33 minus 0.536 gets us an E cell value of 0.794. They might ask you to look at this and decide which one. Well, they gave us our balanced equation, so they're not asking us to decide based on the potentials. But I think in my next example, that is what we're going to do. Okay, so in this next example, we have 2 different oxidation potentials, and we're trying to figure out which one is going to be the reduction and which one's going to be the oxidation. So our E cell, our E value indicates the ease of oxidation. So how easy is it to be oxidized and therefore lose electrons? The more positive the E, the greater tendency to be reduced, and therefore means oxidizing another thing. So the more positive is our reduction. We'll put that in red because it needs to be. More positive is the reduction, and that happens at the cathode. So if you're looking at your values, for instance, we have 2.87 and we have negative 3.05. These are probably the two most, the two highest and lowest values. So you can see that the most positive one is the F, and that is a very strongly oxidizing agent, which means it is reducing. So the most positive is the reduction, and it's at the cathode. And then the most negative value here is the most likely to be the oxidation, and it's at the anode. You could then interpret that and know how to subtract them. So if we had a cell with these two values and we wanted to do our red minus our ox, we would know that our most positive value here is our reduction. So we'd have our 2.87, and our oxidation is our 3.05. And because it's negative, we added that. So our E cell is going to be the sum of these two. Let me do some math in my head here. I'm sure that I'll do it wrong, and somebody will tell me that I can't do math, and I think that's right. 5 carry the 1. Yep. So the E cell for that particular cell would be 5.92.